Hello guys, in this first episode of the video I explained that LLM architecture is same for 3 years except the Muon optimizer. So people who invented Muon optimizer, they probably doubled the speed of AI progress. It's the new optimizer that all of the open source LLMs are using. So if you want to be the next person who's gonna double the speed of progress, who's gonna cut the training cost in half, make neural networks converge in half of the time, then you need to understand the basics. It's not about reading 1,000 AI papers. It's about understanding matrices and determinants and what we will learn in this video. And I think it will not be so difficult because all of the best scientists, they're keeping their research secret and closed in closed source companies. So I think open source is just waiting to invent quite a few new things. But you need to understand the mathematics, what we will learn. And don't worry, mathematics is actually fun. So it's cool and it's fun to read all of the new papers, mixture of recursions, energy transformer, but none of those things end up as frontier, nor do they improve the frontier. The architecture of frontier LLMs is literally same since rope and mixture of experts, except the Muon optimizer. So those things are cool, the papers, but that's not what improves AI. What improves is understanding the math, the matrices, the determinants, understanding why Atom optimizer works, why Muon works better, how backpropagation works in Muon, the determinants, the math, how it interacts with rope, how it interacts with attention mechanism, and all of this stuff we will be learning and mastering in this series. That's what I'm gonna be doing. So you can just follow my channel and we can learn together. And I'll try my best to explain this. So once we master the mathematics and we understand how these optimizers work, then we will be able to invent the next optimizer that's gonna cut the training time and cost in half. It's gonna accelerate the AI progress in half. And other things like replacing rope, replacing tokenizer, replacing attention mechanism, or a mixture of expert neural networks. But it will come from understanding the current things. It will not come from reading new papers. And I would say quite a bit of those students or people who write papers, they don't understand AI in like the deep mathematical level of how everything interacts. And even those few papers that do understand, if you read them and you don't understand the math, the entire thing behind AI, then it will not be so useful for you. You will not be able to invent some big new thing because you don't even understand how the current things work. First, let's understand determinant of a matrix because we need to master matrices. Let's say you have this vector 1, 1 and you multiply it with this matrix 3, 1, 2, 4. What does the determinant mean there? So you can pause the video, but I will show you now. So we're gonna get this. This is the result. So we see that these 3 dots moved here. Okay, so first, let's understand this dot in this corner. So if you just multiply by multiplication, normal multiplication, by this A matrix, you will get 4, 6. So this is the 4, 6 dot. And then what are these 2 dots? So these 2 dots show where these vectors move, these unit vectors. So if you take this unit vector here, after this matrix transforms, so you can imagine it as matrix transforming entire space of this square. So it stretches this side to be like this, and this unit vector, this side, to be like this. So it stretches the sides as it stretches the space. And then the determinant, when you calculate, it will tell you how many times area of this big is bigger than the area of this one. And it will be 10 times. We'll see when we calculate the determinant. You can read this if you want. So to calculate the determinant of this matrix, which will show you how much it stretches the area of whatever the shape you have. Whatever the shape, it will stretch area by this amount. So you go 3 times 4, like this, diagonal, minus the other diagonal, 1 times 2. You get 10. So the area of this shape is going to be 10 times. So now I made A and D minus sign, so now determinant is negative. So this will flip entire coordinate system. So now this shape will get flipped. If I say -1 on diagonal, then the square gets flipped. So this x goes into this x and this y goes into this -y. What will happen if I make determinant 0? So area gets multiplied by 0. So let me put number 2 here, and this will make determinant 0. Can you predict? Okay, it's a line. So now this collapsed, this area, into a single line. So it collapsed 2 dimension into single dimension. So now the problem is you don't know, and you cannot invert this back to this square, to this area. Because, for example, for this vector 0, 1 on x, there are infinitely many vectors that fell onto the same place. So if you do some math, you will realize that all of the vectors with this shape, or these vectors, fell onto the same place as 1, 0 vector. So you don't know, when you want to create a matrix that maps it back from line to this square, you don't know which of those vectors you're actually you are targeting, which one, because so many fell at the same spots, so it's not just one fell there. So for a Muon optimizer, we need to understand inverse of a matrix, because we are approximating it with a polynomial, but we need to understand what it is. So if you have a matrix, it's gonna transform that shape, that space, and then inverse is gonna return back to whatever we started with. So this matrix transforms from this shape to this shape, and the inverse of that matrix will transform this shape back to this shape. So then matrix times its inverse is identity matrix, which is like this, just once on the diagonal. So this will not transform the shape at all. This identity matrix, it doesn't transform the matrix or vector. So if we have matrix times vector x gives vector b, then inverse matrix times vector b gives vector x. But you need to be careful. You need to first check the determinant to see if the matrix is invertible, because if it collapses onto a line or into a lower dimension, then you will have the problem of infinitely many vectors mapping to the same thing as one of the vectors. So the matrix will not be invertible. So you can calculate inverse of a matrix by using this formula for 2 times 2 matrices. And it's a bit tough, so you can check this if you want. I will not for now. So in this case, you get this as inverse, and if you multiply with A, you get identity matrix. If we check example where determinant is 0, first of all, you will have division by 0 here, because you divide by this determinant. But there will be another issue. If you get this set of equations, you get 2 variables but only one equation, because they are linearly dependent on each other, because they are same equation, it's just 2 times here. So you actually have just one equation. So you can get something funny like this, 2 equals 2. Then there is a rank of the matrix. So if we have linearly independent rows, then the matrix will not squish space, remove dimensions into a single line, for example. So it's full rank matrix, because it maps to this space to this space. It has 2 rows and maps to this space, so full rank. But here we have linearly dependent. The second row is just 2x. They lie on the same line. Yeah, they lie on the same line, these 2 vectors. If you try plotting them, you'll see that you have this vector and then 2 times bigger vector on the same line. So rank is 1. And rank is 1 because there is only one linearly independent row. So this row, and then you have 2 times that row and 3 times that row. So only one is linearly independent. So this whole 3D space matrix is going to actually lie on a 1D line, yeah. Because there are 3 dimensions, but they all have only one dimension is linearly, or one vector is linearly independent. So only that line, and then the other vectors will be at the same line. Then let's learn about Frobenius norm. So this is going to calculate length of size of the matrix. So it's just squaring all of the values in the matrix, adding them, and taking root of the result. So I think I don't get this 100%, but geometrical meaning of this is something like how much it stretches the space. It's like a singular scalar value that tells you how much it stretches the space. Of course, matrices can also rotate or squish space, so this norm tells you the strength of this action, whatever it's doing. But I think I don't get it 100%. So there are a few uses for this in machine learning. First, we can kind of measure the size of the matrix, even though I'm not sure what that geometrically means. But if we are trying to keep the numbers in check, not let them grow too big, or we want to normalize the matrix between 0 and 1 or -1 and 1, then we can use this to check the size and magnitude of the matrix. We can use it also as loss function or regularization, where we punish the weights if they become too large. And we can also use it in Muon, for example, in these Newton-Schultz iterations, to check the difference between the current matrix and the desired matrix. This is a quick and easy way to check the difference, and then penalize based on the difference in these lengths. I think it's a lot more clear on an example. So can you calculate the norm of this matrix? I will show you right now. So we just square all of the numbers and then take root, so it's 5. And then we can use this to normalize this matrix, the matrix itself. So we just divide these numbers. We get 3 over 5, 4 over 5 here. So what do you think is going to be now this Frobenius norm? Well, it's going to be 1 because we normalized it. So that's what normalization does. So this is the calculation. So now the strength of this matrix is 1. And we are going to use this in Muon because we want to do this kind of stuff to stabilize the numbers. Because the matrix is going to be same if it's not normalized. It will contribute the same. Maybe even we will have some problems with just big numbers. I mean the same value. So just because there are bigger numbers doesn't mean the value of this contribution to the optimizer is better. Most of the time the numbers are just inflated and they maybe even hurt the performance. So we want to normalize and keep numbers low, between 0 and 1, for example. Now, what we want in Muon Optimizer are orthonormal matrices. So in Muon Optimizer, we are using orthonormal matrices, which means that matrix times its transpose is identity matrix. So that means that transpose is equal to the inverse of the matrix. So in Muon Optimizer, we have some weight matrix, and we have some update matrix that we will subtract from the weights matrix to adjust the weights. This is happening in the back propagation. We calculate the update matrix. So the update matrix can be like this, like 1, 2, and 1004. So this doesn't mean that the back propagation thinks that this exact 1000 here will get the best update. It can just be blown up number because of the multiplications and exploding gradients, not because the back propagation wants this 1000 here. So back propagation maybe wants a not so stretched update. So we will make this matrix orthonormal. I'm also trying to understand this, but we want to have stable training without these huge numbers, for example. So we want to first make the rows normal. So when we do the sum of squares and then root the result, we want to get 1. And we also want to make rows normal to each other. So if we fix this update matrix to be orthonormal, then instead of these random, like exploding huge numbers pushing the updates into some random direction based on these artifacts of multiplication, as opposed to what the backpropagation, as opposed to the transformation that backpropagation wanted us to do with the matrix. So I'm also trying to understand muon, but the way I understand it is we just want to make this matrix orthonormal, so it's not like so stretched in one direction or doesn't have these exploding numbers. And then it turns out that if we update with those orthonormal matrices, you see here loss goes down a lot faster, just because we remove these issues and these artifacts of multiplying like a bunch of big or small numbers. And that's not what backpropagation meant to do. That's gonna be it for this video. I will continue tomorrow, and we need to master these things. So see you next time.